Okay, so what are some of the things we need to consider when it comes to noise? One is our favorite. We talked about this when we
noise.
Yes, when we studied surge coils
Yes.
and flux gates. So the thermal noise of the GMR, okay, is, let's say, SB equals 4 kTr. Okay,
Yeah, because this R is quite large. The quantity
R is the
is not a great one. Yeah.
Yes, of the sensor, right?
Yeah.
And we know this one, temperature.
Yeah.
And K is your
Boltzmann constant.
Boltzmann's constant. Okay, so that's one. Now this thermal noise, well, we are trying to now minimize this, right? But unfortunately, this is always present. Correct? Independent of frequency.
Yes.
What else do we have?
Means it's there throughout the frequency.
It's all the frequency, right? Something it's just there because of this resistance.
Yes.
Okay. You also have now, I think the students, I'm sure they remember, we did the noise analysis with the flux gates.
Yeah.
The 1/f noise. There will be a graph showing this just to refresh their minds. But we also have 1/f noise, which is what? The power spectral density. Right? That is inversely proportional to the frequency. Correct?
For some frequencies.
Yes. Yes.
After that, it is flat.
Yes. Correct. Correct. We'll see that.
That's what I remember.
Yeah, that's true. That's true. That's correct. Yes. Now, what's the dominant 1F noise in this case?
The ferromagnetic material.
No.
Bead.
In fact, it's the GMR elements. So yeah,
That's what I meant. Yeah.
ferromagnetic material. Yes. So the GMR elements. So this one we call contact noise. Okay. So the resistance fluctuations are mainly in the GMR elements.
Yes.
Okay. Why? Because see, we have
you have two ferromagnetic
layers.
Yeah.
Right. Two ferromagnetic layers, and these have domains.
Yes.
Okay. Now, ideally, when you apply magnetic field, right, these domains will nicely change. But what happens is, in generally, even when there's no magnetic field, there could be some thermal fluctuations, right? So if you think about the ferromagnet, there are lots of different domains, lots of different dipole moments. See, for the bead, we are only talking about one domain.
Okay. It's not small.
Yes, because these are nanometer size particles, so they are single domain particles. But your ferromagnet here, even though they are nanometer thick, right, they have several domains. Now, these domains could fluctuate. Now, what happens when you fluctuate?
There will be some change in resistance.
Yes, there will be change in resistance because your resistance depends on the relationship between the pinned and free layers.
Yes. Yeah.
Right. So if they are not properly aligned, let's say, in a certain way, you're going to add some resistance or take away some resistance from your original resistance value, right? So that kind of noise is what we call contact noise. Okay. Right.
The current source, you said you are sending some current.
Yes.
That also may have some
current source. Yes, correct. The current source to what? Excitation.
Excitation.
Yes. We're actually going to talk about that. I think here we have a diagram. Yes. So for low frequencies, okay. the magnetization mono-F, right? Noise is dominant.
Yeah.
Okay. But as you said, at a certain point, what happens?
Maybe the thermal noise will become dominant.
Exactly.
Because 1 by F is reducing.
Exactly.
Over the thing.
At a certain point, mono-F will become smaller. Smaller than the thermal noise. Generally, this is for these kind of chips is about in the kilohertz range. Okay. So when we choose now we have to choose a frequency, right? To excite the bead.
Yeah.
Right. To excite the conducting wire and the current. Right. So this excitation.
Oh, it's not a DC excitation.
No. Right. This excitation current. Actually, frequency. Let's say the frequency of the excitation current. So should be then larger than this 1 over F noise.
Correct.
Right.
That makes sense. Yes.
Then 1 over F. Okay. Because then we want the smallest possible noise. Coming from the sensor. Yes. Okay. What else? Now, that's what we see here. Right? So here, this is your 1 over F noise here. Okay. This is your thermal noise. Now,
which one is the 1 over F?
This is the 1 over F noise of the amplifier. Now, the 1 over F noise of GMR, it's actually...
Oh, that's slope. Okay,
yes.
Okay.
Yes. Because it affects the resistance.
Yes.
Right? So it's kind of moved to where your sensing occurs.
Yeah.
Right? So here, so this is log V frequency. Okay. So Fs here is the sense current. What is the sense current? That is the current that you apply
through the GMR.
Yes, apply to the GMR sensor
to measure the change in resistance. Correct.
Correct. Which you are changing voltage. What else is here? What is Fe?
Excitation.
Excitation. And what's that?
This is the one produces the magnetic field.
Yes. This produces the magnetic field. Now, we also have another one, Fm. What do you think that is? That is the frequency of the magnetic signal from the bead. So stray field.
Okay.
So it's your stray field frequency.
Why that is different from excitation?
That's what we're going to see. Because we want it to be different, right? Because it's embedded in everything here, right? You have your excitation current, magnetic field, sense current, magnetic field. Then you have the noise of the amplifier. Okay. What else do you have?